So the green line you see on the left image is the recorded background spectrum, the baseline spectrum. I'm now gonna reset the spectrum grab. I did it there. Now the gray lines that emerge is the spectrum as it is being grabbed live by the Radiacode. So if I didn't change anything, right now it's not recording anything but the background radiation, it will become like the green line again. I'm now going to get the camera lens and place it right next to the two radiation detectors. The orange radiation detector is a Geiger Müller tube, and the black one at the top is the Radiacode. And you can see the radiation is increasing now from the baseline, which was about 0.7 microsieverts per hour. The window on the right with the yellow dose rate shows the recorded microsieverts per hour by the Radiacode, and the display on the orange Geiger Müller tube, which shows 3.3 at the moment, 3.4, 3.5, is not showing any data on the graphics. It's just the Radiacode that shows the graphics, and the Geiger Müller tube is only showing the display. So you can see the lower Geiger Müller tube is now at 5.2. It has the lens placed right behind it. And the Radiacode is on top of the Geiger Müller tube, so it's a small distance farther away from the lens, and this is the radiation alarm on the Radiacode. And you can see now on the spectrum display the orange part that grows slowly from left to right. Is the orange part is the statistical significant spectrum, so it'll slowly grow as more and more data is grabbed. And you can see some peaks starting to form, but it'll take a little longer before the peaks start to show up significantly. But these peaks will identify, I'm trying to identify one now, what radioisotope is being emitted by the camera lens. And it appears to be Thorium 232. I'm holding the mouse on 238 kilo electrovolts. Right now I'm sliding to the right, and you can see the green lines that form. They show up where the peaks of the Thorium 232 are supposed to line up, and it appears to line up correctly. So initial indications suggest that this is indeed Thorium 232 being emitted from the camera lens. The Geiger Müller tube shows 5.4, and it is the rear element of the camera lens that is pointing towards the Geiger Müller tube. The Radiacode shows 1.16, 1.3 microsieverts per hour, so the Geiger Müller tube is getting more radiation at the moment. I'm now going to change the positions of the two detectors. And you can see how fast the Radiacode is, how fast it shows the increase in radiation. It is the rear element now beaming straight into the Radiacode, and we're up at 12, almost 13 microsieverts per hour. And you can see the orange part on the spectrum is growing quite rapidly now, meaning that sufficient amounts of radiation is being detected for the spectrum to be statistically significant. I'm going to adjust the lighting now so you can better see the display on the Radiacode. That white spot there, I'm going to see if I can move the lamp. As you can see, this lens is pretty hot. I bought this lens in 2014, I think, and it's 2025 now, so 11 years I've had this lens, and I only detected that it was this radioactive yesterday. Trying to line up the peaks now to see, and there you can see the green lines when I hold the mouse. They seem to align correctly with the peaks that match Thorium-232. So it seems correct to assume that this is indeed Thorium-232, which is a known part of old camera lenses. It was banned in the 70s, I believe. I don't know which year this lens is from. As you can see, we get all the way up to 13 microsieverts, almost 14 microsieverts per hour. And this is the rear element. So this is the part of the lens that would point into the camera towards your head when you were taking pictures with it. And I did use the lens a little bit, not a lot, but I did make some photo experiments with it back when I bought it. I don't know if I have used it enough to attain any real radiation effects from it. But of course, as Doctor Who would say, there is no safe level.
Is it safe?
There is no safe level.
But my understanding of the lenses back when I bought it was that I didn't know that it was radioactive at the time. I had a suspicion that it could be because it did have that yellowish brownish tint to the glass. But at that time, my understanding was that it would only be fractions above background levels. And clearly this is a lot more than just fractions of the background level. So it's a lot more radioactive than I actually thought it would be. And I did store it in my living room for, well, at least for 6 or 7, 8 years. I obviously don't do that anymore. Now, Thorium-232 emits mostly alpha particles, so I don't know how dangerous it is to use it on a camera. It's probably not likely that the particles will radiate through the camera and into your eye. But of course, when you handle the lens, putting it on the camera and taking it off and storing it and so on, pulling the focus and all those things, you are obviously close to the lens. And there are also weak gamma radiation being emitted. At least that is how Thorium-232 is described by the US government. You can see the orange part of the spectrum has grown all the way up to almost 1700 kilo electrovolts, which means that the orange part is the statistically significant part. Now I changed the lens so that the front element is pointing towards the Radiacode. You can see how the radiation dropped significantly. So this is the front element. This is the part of the lens that would point away from the camera, away from your head when you were using the lens on the camera. And the Geiger-Müller tube, which stands to the side now a few centimeters away, is all the way down to 0.1 microsieverts, which is the same as the normal baseline background level. So the lens doesn't emit radiation for a great distance. I did a few tests before this video, and it seems that the lens has significant radiation up to about 3 feet or 1 meter away from the rear element. It's mostly the rear element that is radioactive. You get less radiation on the sides and on the front. I'm gonna change the position once again. Now I have it sideways, and you can see it doesn't increase the radiation significantly. It even drops a little. So this is from the side of the lens. So this is mostly where you would have your fingers when you operated the focus and the aperture. Now I'm going to elevate the lens to see if I can get more detection on the Geiger-Müller tube. It's still at 0.2, 0.1. So now the Radiacode dropped even more, because now the lens is, I guess, 6, 7, 8 centimeters above it. So clearly the lens is mostly hot when you're very close to it. As soon as you get about 10 centimeters, 1 foot away from it, the radiation drops significantly, and when you're about 3 to 4 feet, about a meter, maybe a little more than a meter, then you're almost back to normal background radiation. And you can see the dose rate shows 467, that's 0.4 microsieverts per hour. The display is just showing it as nanosieverts. And the peaks are starting to form nicely on the spectrum. We've grabbed 13 minutes of radioactive emissions from the lens and have statistical significance all the way up to 1700 keV. So the Geiger-Müller tube reacts a lot slower than the Radiacode. I discovered that during these experiments. And once again I'm changing the position now. I'm trying to shoot the rear element into the Geiger-Müller tube, but the lens is a bit too high, so the radiation is mostly shooting above the Geiger-Müller tube. But I discovered that the normal Geiger counter, which is the Geiger-Müller tube, the Radiacode is technically a scintillation detector, so it doesn't have a tube inside. The Geiger-Müller tube is very slow compared to the scintillation detector, so it takes several minutes before the Geiger-Müller tube begins to show significant increases in the radiation level, and it doesn't even go as high as the scintillation, so the Radiacode is definitely quicker to detect that radiation is happening. And you can see the peaks line up very correctly with Thorium-232, so I think we can say it's been verified now that this lens is coated with Thorium-232 and that it is, in that sense, technically just another radioactive lens, a basic normal radioactive lens. So nothing sinister. Although, of course, Thorium-232 is sinister enough as it is.
Is it safe?
There is no safe level.
I'm going to change the position once again. Now I'm shooting it sideways into the Geiger-Müller tube. Correction, I'm shooting the rear element into the Geiger-Müller tube and the side is shooting into the Radiacode. You can see the Geiger-Müller tube, how slow it reacts. It's 1.0 now, how slow it is actually building. So right now the lens element, the hottest part of the lens element is actually pointing into the Geiger-Müller tube, so it should increase the most. I don't know exactly how far down the Geiger-Müller tube goes, so we might be at the bottom of the tube. That might be why it doesn't detect as much. Probably the lens should have been a few centimeters higher. But still you can see how slow the Geiger-Müller tube reacts, so this is probably a better device for slow average measurements, where the Radiacode is good for quick detection of radioactive elements if you're sort of hunting which lenses are radioactive. Now I'm moving it 10 centimeters away from the two detectors and you can see how the radiation level drops. This is a little less than a foot of distance. It's about 10 to 12 centimeters right there. So if you were out shopping at a flea market, for example, then the Radiacode, say you were at a stall that had 5 lenses on the table, the Radiacode would be quick to detect which of those 5 lenses would be radioactive, where the Geiger-Müller tube would just show them all as being pretty much the same radiation because it reacts so slowly. You'd need to hold the Geiger-Müller tube on top of each lens for about 2 minutes before you would get a significant radiation detection. And the Radiacode does it in just seconds. Now I have the front element pointing towards the two detectors and the radiation drops even further. So I suppose you could say that if you were taking pictures with this lens, then the person taking the pictures would be the one getting the most of the radiation. The person being photographed would not get the same levels. So you can see the Geiger-Müller tube is almost down to background radiation levels now, 0.1. And now I have the lens sideways, so it shoots sideways into both detectors. Again at about 10 to 12 centimeters away from the two detectors. It looks like the lens is closer to the Radiacode in this image, but it's about the same distance to both detectors. And now I remove the lens back into its casing. And you can see how quick we're back to normal background levels, which is about 0.07 or 0.08 on the Radiacode. The Geiger Müller tube is a bit slow, as you can see it's still at 0.2. The default background radiation level in this location is generally about 0.07, 0.08, 0.09. So the levels you get now, you can see now, are the basic base level. So I believe we can say it's been confirmed, at least sufficiently strongly, that on the peaks here, that it is indeed Thorium-232 that makes this particular lens radioactive. And again, the green line you can see is the normal background radiation, which I had the Radiacode detect for about 6 or 7 hours to build that graph. And you can see it's below the orange code, which is the orange graph, which is now the radiation we built during these past 22 minutes from the lens being radioactive. So a lot more radiation from the lens above so the radiation levels are significantly above the background levels, and of course we saw that. So there are two spectrums showing on the image on the left. The green line is the baseline background normal radiation, and the other graph, the top graph, is what we got from the lens experiments now. You can see we were all the way up to about 12 microsieverts an hour when we were at the hottest. The rear element was shooting straight into the Radiacode. And again the lines, peak lines, align with Thorium-232. And now I restarted it once again, so if I left it running now for 6 or 7 hours, we would be building the same graph as the green line. So that concludes this experiment. And shows one possible way to detect if your lens is indeed coated with Thorium-232, which this lens appears to be. So of course, looking back, I wish I had the Radiacode 10 years ago so I could have known that this lens was this hot. I actually thought that it was just a little bit above. I thought that radioactive lenses were only a little bit above background radiation, but clearly they are significantly above background radiation. And I'm gonna end this video in just a few moments.